in 1 minute. Okay, welcome to this last afternoon session. We're going to start with Antonio Pensabene, who's going to give us a talk about witnessing the assembly of galaxies in a massive node of the cosmic web at Redshift 3. Please.
Okay, thank you. Hi, everybody. I'm starting to like to be the last talk of the conference, so by the way, I would like to thank the organizer for giving me the opportunity to present my work here. So I introduce myself. I'm Antonio Pensabene, postdoctoral researcher at University of Milano Bicocca. Here are the name of my main collaborators, in particular Sebastiano Cantalupo, which is the PI of the project. And today I'm going to show you some results based on ALMA observation toward a massive node of the cosmic web at redshift around 3. The story began with this outstanding discovery of the largest contiguous cosmic web filaments found so far, emitting Lyman alpha radiation. On the left you can see this Muse mosaic, very deep observation covering a patch of the sky of 4 co-moving megaparsec. You can clearly see intergalactic gas filaments converging toward a node in the proximity of type 1 AGN quasar actually, which is located at redshift 3.25. So on the right is the same patch of the sky, but is an optical broadband image with the Lyman alpha contour superimposed. And all these yellow squares are Lyman break galaxies selected with Muse, which lie in a very narrow redshift range, and all lie or are embedded in this gigantic structure. We also have some type 2 AGN candidates, which are these red squares, which formed together with the quasar in the node a unique AGN triplet at redshift 3.25. So it is clear that this is outstanding, a perfect laboratory to study how galaxies assemble their mass around cosmic noon and how they evolve in the densest part of the universe. Therefore, we started an observational campaign using multiple facilities in order to try to get a panchromatic view of this interesting structure. And in particular today, I'm going to show you some results based on some millimeter observation with ALMA. ALMA observations are crucial because star formation can be often accompanied by heavy dust obscuration, making some Lyman break galaxies completely undetected, even in very deep rest frame UV observation. Therefore, we want to obtain a complete census of star forming and dust obscure galaxies within and around the filament, with the aim of try to correlate the galaxy's gas properties, such as the gas content and location of galaxies, with the filament properties as traced by Lyman alpha, such as density and kinematics of the intergalactic gas, in order to shed light on how galaxies accrete their gas at high redshift. In addition to these, we also obtain a high-resolution single-pointing ALMA observation toward the node of the cosmic web to study in details the morphology and kinematics of the galaxy called gas, where the highest concentration of galaxies has been found. So let's go directly to some results. Here in this animation, you can see JWST NIRCam image covering the field. In gray color scale, you can see also the location of the Lyman alpha gigantic structure. And violet crosses are the Muse-selected Lyman break galaxies, which, as you can see, all lie embedded in these gigantic filaments. So with ALMA, we perform a couple of mosaics observation covering the entire field surveyed with Muse, and we discovered 11 CO423 line emitter, including a closely separated quasar companion, which is located just 1 arc second south to the quasar. Interestingly, some of these galaxies also are extremely extended. We didn't expect to discover such gigantic galaxies. Indeed, the mosaics were designed in order to do not resolve the emission of the galaxies. And this is an example of a very big galaxy that is located in this Lyman alpha blob. Together with the ALMA band 3 mosaic to target the CO423 line, we also use ALMA in band 6 to target the 1.2 millimeter dust continuum, and we found that some counterparts of these galaxies, and in particular one, which this C08, for which the mu spectroscopic redshift placed this galaxy in the same narrow redshift range. Here I show you the spectra, the line emission of the different galaxies, starting from the top, which is the quasar host. This is the companion of the quasar. This is the gigantic galaxies that I showed you before. And as you can see, all these galaxies lie within plus minus 1,000 kilometers with respect to the quasar systemic redshift, and therefore immediately pointing to a huge overdensity of CO emitter in the structure. Some of these galaxies are very gas-rich. If we convert the CO423 luminosity in molecular gas mass by assuming appropriate assumption, we found that molecular gas mass is up to 5 times 10 to the 10 solar masses. Other galaxies are very dusty, so showing the crucial role of sub-millimeter imaging toward dense structure of the universe at high redshift. And then here I just wrapped one example of galaxies completely undetected in the rest frame UV. This is the Muse white light image. Contours are the CO423 line. And these galaxies start to be detected if we go toward the near-infrared part of the spectrum using JWST NIRCam. Okay, so in order to understand what is happening in this field, we studied the CO423 luminosity function, therefore the galaxy volume density per unit of luminosity beam. So what has been measured in blank field is reported in blue and greens. These are data from Aspect's large program and another NOEMA program in the Hubble Deep Field North. And this is the CO luminosity function in blank field. What we measure is instead reported in red and yellow in different redshift beam. And as you can see, there is a clear excess in the normalization due to the overdensity of galaxies, so larger number counts of galaxies in the field. But then there is a trend that reminds the trend observed in blank field, but then we see a flattening at the high luminosity end that is also enhanced if we take in account only galaxies lying within plus minus 1,000 kilometers per second. By doing the ratio between the measured CO luminosity function and the one observed in blank field, we computed the cumulative overdensity function, which is reported in this panel. And as you can see, by taking in account all galaxies, we found an overdensity of CO emitter of at least 15, which increases faster as far as we take in account only more luminous galaxies. We interpreted these results as an excess of more massive galaxies and probably a larger amount of molecular gas that is supplying the star formation in this system, and therefore accelerating the galaxy assembly. If we put together all the mass that we have in galaxies and we compare with the molecular gas density across the cosmic time, we found that MQN01, that is the name of this field, lie at least one order of magnitude higher with respect to the expected value in blank field, and is also compatible with the largest structure at later time, such as the spiderweb protocluster. Then we also try to do the same experiment by using the dust continuum selected galaxies. Therefore, we studied the number counts of galaxies as a function of the flux density measured at 1.2 millimeter. In this case, the statistics is lower, implying large uncertainty, but overall, if we compare with the blank field again, reported by Aspects, we see an excess in the normalization. And interestingly, This trend is also very similar to what has been observed in SSA22, which is another famous protocluster, also showing filaments of Lyman alpha on large scales of a few comoving megaparsec. If we compute the cumulative overdensity again, we have large uncertainty, but overall we found values that are consistent with what we previously found using CO line. In this case, we argue that not only the star formation is enhanced due to the larger amount of molecular gas supply, but also the obscure star formation and metal production activity are enhanced in this galaxy-rich environment. Then we studied the membership of the objects in this field. We computed a halo mass, which is of the order of 2 times 10 to the 12 solar mass with a virial radius of 100 kpc. And if we put our object in this phase space diagram reporting the line of sight velocity of galaxies as a function of the projected radius with respect to the center of the structure, we found the evidence for an existence of a protocluster core. So these objects are expected to be bound in the system and form a core of the protocluster. In addition, we also found a group of galaxies exhibiting low line of sight velocity, which also lie in the proximity of the so-called turnaround radius, which is the distance at which galaxies are expected to be detached from the gravitational potential well and be dragged by the Hubble flow. And so overall the entire structure seems to be not virialized, but maybe we are witnessing the phase in which multiple subhalos are starting to collapse toward the protocluster core. Now I briefly show you some results that we are obtaining using the high angular resolution album observation, again targeting CO423 line in the node of the cosmic web. As I told you, we found a companion galaxy of the quasar, which is located just 1 arcsecond south to the quasar host, which was completely outshined by the quasar PSF in rest frame UV observation. Here the CO423 map, you can see the companion of galaxies is even brighter than the quasar host and also shows a double-peaked profile in the molecular gas, probably indicating a ring-like structure that we are seeing at a high inclination. We studied the kinematics. Here the kinematics of the companion galaxies. The velocity field seems to be quite regular, indicating the presence of rotationally supported disk. We modeled these kinematics by using 3D Barolo, and here the PV diagram, which is totally consistent with the rotating disk. And this object is extremely massive. The dynamical mass within the inner 4 kpc is around 10 to the 11 solar masses. The quasar host show a disturbed kinematics. There is probably a hint of velocity gradient along this major axis, but then we have other feature indicating the presence of non-circular motions. And this is probably, we are witnessing an interaction between these two systems. It is interesting because in the quasar host, we also found the presence of a blue-shifted broad wing. This is the spectrum of the quasar host, the CO423 line. And interestingly, if we take in account, if we try to model the kinematics of the quasar host with a thin rotating disk, we found that there is a large amount of, there is a huge contribution of random motion. If we take in account this random motion in the computing the dynamical mass, we found that actually the quasar host is not the most massive object. If we look at the channel maps of the residual, therefore after subtracting the thin disk model, we found this feature, and this could be a spatially resolved massive molecular outflow or just the feature of an ongoing merger, but this investigation is ongoing. Then finally, by combining the mosaic and the high resolution observation, we also detected one of the type 2 AGN forming the AGN triplet around the cosmic web node. And interestingly, we have also the CO928 for this type 2 AGN, so supporting the evidence that this is actually an AGN. And so we have the opportunity also to study the molecular gas excitation in this very dense environment. So what I show you today is just part of the story. These are results based on far infrared data from ALMA, but as I told you at the beginning of my talk, we surveyed this field with multiple facilities, therefore with ALMA, but down to the X-ray using Chandra. And so the best is yet to come. Stay tuned, and I thank you for your attention, and I leave you with my summary and future outlook. Thanks.
Antonio?
When you looked at the overdensity in CO, was the aspect survey also looking at CO4 to 3 at the same redshift, or were you comparing to different transitions?
No, definitely. We use aspect. We employ the catalog from aspects reporting CO4 to 3 emitter at similar redshift. Yeah, of course.
4 to 3 is also quite sensitive to the dust temperature or the gas temperature. So do you have any hints? Do you have any other transitions that let you understand whether or not the excitation is also different in these protocluster galaxies?
Unfortunately, we have two mosaics in band 3 to cover the CO4 to 3, and the band 6 that was designed to cover the 1.2 millimeter dust continuum, but which also cover actually the CO928. In some of galaxies, especially in type 2 in the AGN, we also in the quasar host, we have also the CO928, yes. But unfortunately, we have just a couple of objects for which we have this line, but we will try to compare the with two transitions, the CO SLED with the CO SLED of galaxies living in isolation at similar epochs.
Thank you.
Yeah, thanks. It's a great work. So since you have a high resolution CO4 to 3 line, you can probably derive the dynamical mass and compare with the stellar mass plus stellar mass, and then you can possibly constrain the alpha CO. Have you tried doing that?
Well,
or so, which value did you apply for alpha CO?
Yeah, thanks you for this question. Yeah, so we are working in deriving actually the stellar mass for galaxies in this field because we have multi-wavelength data. So we are doing the SED fitting to derive the stellar mass, and yeah, it's definitely something that we can try to do. Yeah, thanks.
Okay. So,
now that you've all eaten too much food for maybe the 10th or 15th time in a row this week, hopefully, and maybe had your 173rd espresso, hopefully we can, hopefully we can have a vigorous discussion. So, we have to first say that Barbara Cantanella was supposed to be part of this, but she's not feeling well, so she couldn't show up, so we're going to do our best to fuddle through this without her input. What we thought we would do for this discussion is actually in format quite similar to what the last discussion did. We'll have 3 general science areas. We have a panel selected for each one of the science areas, and then we'll ask them some questions and then have discussion with the audience. So for each one of these, we want you to think about this, and also we've told the panelists to think about this. 2 questions. First of all, which is what is kind of the most surprising or interesting thing that you've learned at this meeting in this area? And as you can see, this is a very broad area. I mean, Benedetta's review talk had to cover 40 years of astronomy, and it's a big area. So we've tried to focus on a few things that were very relevant to this meeting. So one is what's one surprising or even just very exciting thing you've learned? And the second is, did any questions get raised for you that you would like to address by the time we have GASPISA 2029, which I've heard is definitely going to happen. So we have 3 panels, and the first panel, we have, now I'm going to get the first name, Elad Zinger and Patti Romazzocco, and then Luca Cortesi. If you guys could come up. And so this first topic is what quenches galaxy. Oh, you're doing this. Yeah, you do this. I'm not doing this. I'm doing the next one.
Come on, Patti. Yeah, so the idea was to start with groups. There have been a lot of discussion about groups, about all the environments, but in particular on groups. So the question there, the first starting point of this discussion is quite broad. So what are the most effective environmental quenching mechanisms in groups? Benedetta gives a very nice review about what happens in cluster. But yeah, I think it's interesting also for the future to trying to move out of cluster and trying to focus on groups. And another interesting for us point is that, okay, so everything we have learned so far in cluster, how is that relevant for this question? So to understanding what's going on, so what are the physical mechanisms driving galaxy evolution in groups? So if the panelists have some thoughts on some of these aspects, and anybody of you, of course, is more than encouraged to participate. So if you want, we can start from a theoretical point of view.
So going back to this, what would I like answered in the future? And I have many things I'd like answered in the future. But one specific things in groups and environment that's kind of, I'm not sure it's clear, is what, if any, is the effect on the environment inside the group, which is set by the large-scale structure, and how does that change over time? Groups today are probably going to be found inside filaments, but at higher redshift they were nodes. And would that have any effect on their CGN basically in that environment, and how does that affect the quenching processes? So that's something that I would like to somebody to tell me. Oh, nobody here. No, you haven't heard a word of what I've said. But if somebody disagrees, then let me know. Or if you think it's not important at all.
Want you to comment on that?
Hmm?
No.
Oh, there's somebody there.
Oh, sorry, I haven't seen it.
So a word that didn't appear at all, or very, very rarely during this meeting, is the role of mergers. No, that may be important in group. What do you think about it? I mean, we stopped talking about merger for a while, and I was wondering whether we believe that they are not important or they are important only in particular cases. What about mergers in groups?
Mergers between satellites and groups?
Yeah.
Or mergers in general?
No, more mergers in general is a quenching mechanism, but then applied to galaxies in groups in particular.
I mean, it's true, we've not been focused on that. I think a lot of people kind of, we've done mergers, we know what they do, but we know that they can shoot up, but I definitely think, of course, this is something that's working in tandem with everything else that's going on. It's one of these, multi-process things. Definitely it should be taken into account in terms of what is more important or not. I'm not sure.
I think I agree with you, Antonino, that we don't talk a lot about mergers. I think it was Nadine Hank who gave a short talk and presented a poster where she was mentioning that in her simulations, she was finding that mergers were more driving the asymmetries that she was seeing in galaxy filaments as opposed to the global filaments themselves. But I think, yeah, we kind of sort of gloss over them. But we do talk about tidal interactions with that kind of like gravitational as well. The one thing that I would actually like to ask the people who are actually quantifying mergers and were saying that they are only looking at projection effect, is there a way to sort of fold into your models spectral information as well in these quantifications of tidal interaction and RAM pressure stripping? I'm looking at Ji-Wang.
I suppose that, yeah, spectral would be great. Like, for example, we can see like how the stripping, how gas is stripped away, because like we know it has been stripped away, but how? Like from what it is simply evaporated, is dragged away, then it go away. It mixed with CGM or IGM. And with this, I suppose the like temperature information, the ionization state could be very helpful, indeed. And yes, and another effect, like we not only the tidal interaction between galaxies, but also tidal interaction with the much larger potential well. I think there is a lot of things we could consider. And also in regarding the so-called most effective, how can we say this is more effective? In the most, if we count among all of the quenched galaxies, like if 60% of them are quenched by this mechanism, then perhaps we can say this is the most effective. But what if actually the galaxies that is influenced by such a mechanism is much, much more? So for example, if there are 1,000 of galaxies that is influenced by this mechanism, but only these 60 galaxies are actually quenched, then it is not that effective. So which the parent sample we want to count. That's also how can we say it is most effective. Yeah.
I also wanted to add that I'm not sure we are yet in the position of establishing which is the most effective, also because with MUSE in general, with GASP, we have seen that only with spatially resolved data we can establish which is the mechanisms, but we don't have a group sample that is big enough to really statistically and significantly address which are the different mechanisms. We have some results, I don't know, Matteo Fossati with the group field, the group, big group, I'm sorry. They characterize some specific groups, but we don't have a full sample that we can establish. Well, first of all, as you said, it could be that many galaxies are affected by mechanisms, but they are not quenched yet. But we don't have the statistics to do it as a function of group mass, stellar mass. So I think we are still far from knowing what is the most effective mechanisms in groups.
So can I just ask, do you think then that you would like in 5 years to have GASP2 plus, so a big Muse survey of 10 times in size? Is that the kind of thing you're advocating for?
Yes, I think that it's a lot of work because we need a big sample. We need to cover many groups of different size, galaxies of different star-forming properties, but I think that that would be the thing that it's needed.
Maybe not with me.
I agree and disagree with this because you definitely need bigger sample, result data, etc. But I don't think Muse or an optical IFU is really what we need as a community, also because in groups time scales are significantly longer. So getting the smoking gun like the jellyfish or the stripping is going to be much, much, much more difficult. And this is why there is a challenge in groups, because we don't have to forget that most of what we know about quenching groups, and we know a lot, is still based on the beautiful work that, let's say, spectroscopic surveys have done in the last 20 years in terms of quenching fraction and quenching time scales, etc. Of course, everything there is not resolved, and we are missing the gas. For the groups, we have no idea what the gas is doing.
The CGM gas.
No, even just the H1 and the CO.
No, but the gas inside the galaxies, or the gas?
Both.
Both.
In a different direction from my comment, so I'm not sure I should make it now. Are you going to cover filaments as well later? Okay, then I'll get the mic later.
So going back to mergers, I think there's actually a lot of work to be done on mergers, and I think that could be somewhere where the group environment is very useful. I mean, the velocities are favorable for mergers or interactions in the group environment, and I think part of the problem with our ability to look at mergers so far has been that a lot of the consequences of mergers, any sort of triggered starburst or black hole accretion, happens generally associated with the late stage merger, which also happens to be the dusty phase a lot of the time. So we've had a really hard time identifying late state mergers, and now with JWST groups are so much smaller than clusters on the sky that we can actually go and get pretty good samples and then look at the merger rates and the consequences of mergers with rest frame near infrared that's pretty can get at these late state mergers a little bit better. So I actually think that's a place where we could make some progress.
I'd like to pick a fight with Luca a little bit. Because I think that there might be lots of short time scale things going on, like satellite accretion and things like that we just don't pick it up because we don't have the right data, right? So yes, in groups, yes. So I think that the fact that the time scales are long and then you don't get the data because you will not have the smoking guns so easily, I don't think it's a nice point, because there might be smoking guns that we just don't know are there, right?
Agreed. You can look at the thing from two different point of views. Of course, we have a lot of groups. Look at the local group. Look at the Magellanic Clouds. Look at the Stefan Quintet. We can list them, and we know there that in particular when you look at the result point of view, you could argue, you see them, the region where you have the poster bust region inside the disk, and US stripping, short-term stripping, and short time quenching time scale, etc. I think it's pretty much established that from a global point of view, the quenching time scale statistically in groups is longer than in clusters, because then that's the main problem that we have. I'm not saying it's impossible. I'm saying that even in clusters, look, we are still working on a limited number of clusters for which we can do this multi-phase, multi-scale analysis. And when it comes to groups, you need even more statistics. I'm not saying it's impossible. I'm just saying that you need to multiply a survey like GASP by 100 to really nail it down.
Which would be very cool, though.
Yeah.
So you're saying that we need a survey that is GASP times 100. There's no other way out.
I think you need a resolved one. I'm not sure. I would personally go for the IFU to start with. I would
No, me neither.
I would go. You need something that is
Okay.
a representative sample of, I would say, 10 to the 13 elo masses to start with,
Yeah.
and go with that.
It's going to be expensive, but
Yeah,
I think
sure.
it's the only way out. Yeah, sure.
So maybe I'm behind on the times. Is there no pathway to rapid quenching of lower mass galaxies that have shallower potential wells just through gas stripping in
Yes.
group environments?
Yeah, this is pretty much a local group. I think Paolo showed the beautiful plot by Mary Patman and co, where you look at the MH1 versus the instance from there. Absolutely. Again, everything is multidimensional. If you go to the dwarfs, I would argue the groups we understand them in terms of stripping, and stripping is very important even in the groups. If you're talking about 10 to the 9.5 and higher stellar masses, I personally don't understand yet what's going on there.
But if you look at modeling passive fractions, so Tim Carlton and Tay Baxter have done this where they've modeled low mass galaxies and groups in the local universe, and they find that the quenching time scale is mass dependent, such that it's shortest for the most massive galaxies, it's longer for low mass galaxies, and it's not until you get to very low masses, like, ultra-faint dwarf galaxies, where it really drops down again. So I think that's tricky. We think they're shallow potentials, but if you model the buildup of the passive fractions, it looks like the quenching time scales are long. I think that one thing that was interesting in terms of combining these processes is what Mapati had talked about in her talk, that if you have mergers, this is coming back to the merger idea, the mergers can actually enhance the other mechanisms. So if you have minor mergers, it can unbound the H1 more and then make it easier to strip in environments where you wouldn't normally associate it with being stripped. But we don't know if that's a dominant quenching mechanism or just a mechanism. Should we go to the next one? Or do we have any more? Oh, Nadine, did you want to say something? And then
So just to add on that point, but not necessarily in the context of mergers.
I think the microphone is off.
Hello?
Yeah, better.
Is it okay? But not in the context necessarily of mergers, but I think a few people on case-by-case basis have shown that tidal interactions maybe happen before ram pressure stripping. And so I guess in environments where interactions are common in these dense environments or even in groups, to have a statistical analysis of whether there is a difference between galaxies or the timescales that galaxies will experience ram pressure stripping if they only experience ram pressure stripping versus if they were to have an interaction before their gas is stripped, if that makes sense.
yeah, I wonder if one possibility for that is that if you get stellar kinematics, which should trace the interaction history better than, independently of gas kinematics, because hydrodynamic effects will only affect the gas. I wonder if you could detect stellar kinematic asymmetries that would then identify mergers. So in ram pressure stripped galaxies where you wouldn't expect the stars to be disturbed at all, you could see whether or not the stellar kinematics were messed up. I just made that up. I have no idea if it's true, but it...
You see it easier with optical morphologies. I think it's easier to spot these interactions at the outskirts of the stellar body.
I think we should move to the next. So thank our panel. So our next panel is Why Do Filaments Matter? And we will have, I forget first names. Nick Luber, sorry. And Nadia Zakharova and Benjamin Seidel. Sorry. We see who matters too. Okay, so keeping on the group, and we obviously have a group-centric thing here, partly because we feel that clusters have been done a lot and the technology and the surveys are enabling us to address these questions better. So one question would be, do filaments pre-process group galaxies? We always think of pre-processing in terms of cluster populations and groups as the things that pre-process, but the filaments actually pre-process group galaxies. And second, the galaxies spend most of their lives in filaments, and how does that play a role in their evolution? Those are kind of big questions, but that's where we're going to start with. Would any of the panelists want to say something?
I would also add that our definition of environment really depends on the time scale, the time when we defining it, and the process which regulate galaxy evolution and galaxy process really depends on the evolution of the large-scale structure at that time. So we need to understand better how large-scale structure evolve with these galaxies, because this co-evolution cannot be disentangled. And also Katerina showed in her talk about that galaxies inside filaments have different evolutionary paths. So we need to take into account this effect during the whole evolution, not just when galaxy became in filaments or its life spends the entire life in the filaments.
Does anybody have a comment on that?
Yeah, so for the first question, like do filaments pre-process group galaxies? I think trying to answer that observationally will be extremely difficult, just based on my experience looking at groups in filaments. It's kind of like which came first, almost like when you only see the effects on the galaxies, but you don't know whether that is due to the filaments themselves, like if the filaments themselves affected the galaxies first or the groups affected the galaxies first. So which one happened first, I think you might need simulations. I mean, you'll probably need simulations to be able to tell that. I had another point, but I can't think of it right now. Yeah, I think also I remember what it was. I think in Katerina's talk, she spoke a lot about the spin properties and their alignments with filaments. And yeah, there have been some really good papers, I think, trying to look at that and measure that observationally. And yeah, I think I might be referencing some of Katerina's work, but I can't remember if she spoke about it or not, or if it's just stuff that I read. But kind of the alignments between galaxies and their host filaments and kind of their H1, their spin alignments and their H1 masses. I think there was some interesting work. Can't remember again if it was from simulations or if there was some observational.
There is some observational.
Yeah.
From Chiles and Mighty, they have two different papers.
Yeah, about the H1 mass, like the transition in H1 mass and spin alignment. So that might be something that may help us answer that first question. But yeah, I don't know how the spin alignment changes when you get into the group. When you get into groups, so yeah.
Does anybody here have, there's some interesting stuff that she said. Anybody here have a comment on that?
I think that the different effects that filaments have on like galaxy evolution and the different ways they can affect them, that really goes back also to what Daria said, is the dynamical state of the filament. So whether it can affect galaxies via its, like if you fall into a hot filament and into a dynamically evolved filament, it might make a huge difference versus falling into a relatively underdeveloped young filament where you still might get the gravitational effects, like you said, the spin alignment in the vicinity of filaments. So I think it's going to be really important to really figure out the evolution and to really acknowledge the diversity that filamentary environments can provide in dynamical state and even gravitational setup, because the answer is always, with filaments, I feel like the answer is always more complex than you think when you ask it in the first place, because they come in different sizes, they come in different dynamical states, they affect, even going back to what also Elad said, maybe pre-processing or like group, how the filaments affect groups. Like if you start out as a node in the cosmic web and then you become a galaxy infalling within a filament, that might also affect like secondary effects, like setting merger geometries differently. So I think, with filaments the problem is that they are connected to a lot of different processes, and it's going to be hard to disentangle them. I think that's more on the numerical side than the observational side, because most of these effects are pretty hard to observe currently, I would think.
I can say what I wanted to say before. It's exactly on this point of alignments in filaments, which I think ties up with what Antonino was saying about mergers. So one thing I thought I understood where both simulations and observations are starting to agree is indeed this alignment, and in particular the fact that the late-type galaxies or the star-forming galaxies have their spin that is aligned along the filament, right? While more massive galaxies, but in particular what struck me was in Katarina's talk, lenticular galaxies have their spin perpendicular to the filament. And that is because, my understanding at least, is because you accrete, matter is flowing into the filament, gas from the large-scale structure is coming into the filament from outside, of course. And so this galaxy starts spinning with their angular momentum along the filament, but they merge with one another moving along the filament, and so the angular momentum of the merger as a wall is actually perpendicular to the filament. So the fact that lenticular galaxies have they are aligned preferentially perpendicular to the filament, to me, is saying that the way you're making lenticular galaxies, the way you're quenching a galaxy is through mergers. That's why I think this ties with what Antonino is saying, right? Otherwise, if you are quenching galaxies in filaments through things that have nothing to do with merging activity, there shouldn't be any preferential alignment of lenticulars along filaments.
Well, unless gas accretion and the efficiency of gas accretion depends on how the galaxies couple to the angular momentum of the gas in the filaments. But maybe that's a second order effect, because the merger would be a much bigger one. I don't know.
So if once again I'm looking to the future, to 2029, I think one of the things that we're really missing in the question of this filaments and the large-scale structure in general is mainly constraining what the environment inside filaments is. I mean, for halos, we know when they're hot, we know when they're cold, we have models for accretion shocks and all of these things, and if I give you a mass, then you know exactly what it is, but we still don't have good, simulations. We're only starting to get simulations where looking in this direction and observations. I'm not an expert, but I'm sure it's very hard to do observations on something you're not sure is even there. But I think that's something we should be looking forward to, doing this work of understanding where you'd expect the filament to be hot, where you'd expect it to be cold, what would be the temperatures, what would be the gas profiles. Filaments can merge just like halos can, and what does that mean for the galaxies inside them? What are the timescales? I think there's a lot of work on constraining the filament regime, which still needs to be done. A lot by simulations, and hopefully that could point the way for observations as well.
Okay, has his hand up.
Look, just go back to the last 2 points. I agree with what Paolo said, that this tantalizing evidence of alignment or misalignment of angular momentum, it's very interesting, but we should remember that it's not perpendicular or parallel. We're talking about a few degrees of difference in the spin alignment. It's closer to parallel and it's closer to perpendicular, but it's not that one is 90 degrees and the other is parallel, are very subtle effects. So this brings me to Daria's point and Daria's talk. To me, what Darius has shown is that to first order, once we control for group environment, the filaments is a second order or third order effects. We don't see, even in models, effects of filaments once we control for group. It doesn't mean, I'm not saying filaments are not great, but we can start building a ranking. And third point is, if a galaxy is not in a filament, is not in a group, is not in a node, what am I working with to have my control sample? Because then we start entering into semantic. Because of course, all the galaxies are in filaments in the end, apart from voids. Somebody said that voids are not interesting. But I think we need also to be careful to remain attached to the physics and to the question that we're trying to answer. The universe is very complicated. If we start dissecting everything, then of course everything depends on everything, but then what are we actually trying to answer?
So I think that, from an observational standpoint, it's very hard to understand the gas in the filaments just because we don't have the ability to see that it's not hot enough and dense enough for us to see. But if you have really high spectroscopic sampling, you can actually identify groups as like beads on a string in the filament, and you can decompose galaxies. Daria has shown this in her talk. We've done it in the Virgo filament survey. It's hard though. You need lots of spectra to do it. And then you can start asking, do the filaments galaxies look different than a control, where you might say the control are isolated galaxies, so things like from the Amiga survey or something, where things are really isolated, so they're the void galaxies nobody cares about, but don't tell that to all the people who have void conferences. But so I think there's observationally a way to separate those things. But there's a philosophical question. Are filaments an environment that's intermediate between voids and groups, or are they just the place that every galaxy's in before they enter a denser place? And so I don't, does pre-processing even mean anything if it's the place you've been your whole life until you move into the big city? I don't know.
Well, as somebody who lives in a big city, you can tell the people who are new. So.
Yeah.
But I also, just to shift gears a little bit, I really like, your point is what I was thinking when somebody asked, or when the question was, what do you want to know in GASPISA 2029, is what is a filament? I mean, we're talking about this, ad nauseum. And, you can go to a cluster. If I took a cup full of cluster, I know what would be in the cup. But if I took a cup full of filament, I have not the slightest idea from a simulation or an observation what I would find. Is the gas hot, cold? What is the fraction of it? What else is just lying around? And I mean, of course, there's some idea. And that's what I want to see is, for all of the observers, I want to see detections of the gas in the filaments. And then from the simulators, I want to know how big filaments are, radial profiles with mass, and how that goes with their lengths and the environment of the galaxies around them. I think that that's really important for us to understand any of this. And like in my talk, I said that the filaments are 3 megaparsecs. I mean, that's just throwing crap against the wall and seeing what sticks. But and I'd like to constrain it more. So I'll just throw.
I mean,
that
people
out
have stacked Sunyaev-Zeldovich between LRGs. They find a very robust detection of the gas and filaments in a statistical sense.
Yeah.
Right? And I think we can, in the simulations, if you look at the gas in the simulations, you go to hydrangea and the filaments are extremely apparent in the gas. The question is, how do you find it observationally?
Yeah.
And how do you associate it? So things like running your filament finders on the simulations and the observations may be the way to go, and you're neither complete nor pure, but at least you're equally impure and equally incomplete.
But simulations don't throw resolution at filaments, they throw them at galaxies. So that's something that has to change.
Yeah.
You should start.
Yeah. We have.
I would like to expand on the comment that he made on the filaments. What exactly are these? What I wanted to raise was that most of these filament finding algorithms don't agree with themselves. You have most of the people using Disperse, which was written in 2011. And after that, there have been many attempts of making a filament finding algorithm itself, like Nexus Plus, for example. But they don't agree what a filament is in itself. So if you apply it to the same simulation, so there was a seminal paper in 2018 by Noam discussing different various filament finding algorithms and how do they agree with themselves. And they found out that the results are completely different depending upon which filament finder you are using. And so therefore the question comes in, what is a filament in itself? It depends on the filament finding algorithm that you're using. And of course these are algorithms, so you can tune the parameters to match them with each other. But then if one person is using one filament finding algorithm, how do we know what a filament is? There's no one truth in the filament itself.
Which was exactly like the last statement of my talk. Yeah, that in Chili's we run Disperse, just like the website tells us to, and we find that voids have no gas, which of course is deeply wrong. But it's the best we can do, and I think it's interesting if you compare it to I forget their name, a Dutch name, and they do the watershed finder, and they find these voids, and we find the exact opposite. And at the end of the day, what are we actually looking at? What is my cup full of filament full of?
if we're in stage of criticizing filament edification, I would add that filament edification in the simulations and in observation is completely different task due to peculiar velocities and distortion of over the sample. So it's even harder than it seems to be.
So Moons wants to find filaments in case, and Weave and Foremost, right? There's whole programs to find filaments. So should we tell them to do something else? Is there hope in these? Right?
We just have to tell them to be sufficiently clever.
Yeah, maybe by 2029, having reliable tracers for filaments would be a good point on the wish list. And maybe even like, also there's always this multi-scalarity to the problem. With disperse in a simulation, I can get 10 different answers based on the question I'm asking. So this is, I think, a bad state to be in, even purely keeping to theory already, because I might get like a broad variety of different results based on the parameters I set for running disperse. So yeah, the multi-scalarity is also, I think, a huge problem that needs to be addressed from the theoretical side probably.
Yeah, my suggestion is the same, to explore more large-scale structure in its evolution, to apply to galaxy evolution.
Yeah, maybe tie what you find in numerically or in simulations to the dynamical states of the actual filaments you get out, to the gas properties, something like that.
I think we should. Yeah. Thank you very much. That was a good discussion. Yeah, my mouse. Okay, so now we have Benedetta Vulcani, Lami Marad, and Stacy Alberts coming to answer the question, environmental quenching at high Z, why does it matter? And so, yeah, if it matters, why does it matter? Maybe it does matter, in which case it really matters. So, for example, two ways of drilling down on this are, what can we learn about Z of 0 environmental quenching questions or transformation questions from the things we're learning at higher redshift? Are they a tool just to learn about higher redshift, or can we also use that information to learn more about low redshift? And then, if we want to understand gastrophysics at high redshift, how the baryons respond to dense environments, and if most of the gas in the universe is H1, and we can't measure H1 beyond some intermediate redshift, what progress can we make? How do we attack these problems? So I'm going to just let them answer these questions.
Okay, I have, for the first one, one of the things that we're going to be able to do even better than we have before is spatially resolved studies, spatially resolved SED fitting, looking at star formation histories. And one of the nice things about looking at star formation histories at higher redshift galaxies is that they've had less history. So if you look at the star formation histories of quenched galaxies, you have a little bit easier time interpreting them. So that might be something that we can apply at higher redshift easier than we can apply at redshift 0 in that one sense.
But if I find out what quenches a galaxy in an overdensity, I'm just going to say overdensity because we don't really know how these things evolve, down to Z of, at Z of 2, 2.5, do I learn something about quenching at Z less than a half, or is that not the point?
Well, but we will finally be able to prove the scenario in which there is a primordial versus quench population. If we are able to understand actually how higher redshift galaxies quench, we can understand then the contribution of the quench population later on. So.
I agree, but
Yeah.
I wanted to be controversial.
I mean, there's also timescales involved that, we might actually be able to pin down using that star formation histories. So, yeah, that's my one thing.
Do you
But
think
now Lamin's going to tell us that there is no environmental quenching at high redshift.
Ooh, controversy.
I don't know, will she?
Well, not really. I mean, what my work, what we found is that it is environmental quenching in the sense that it's different in different environments. It's just not the way we understand environmental quenching. It's not just like, say, gas stripping. It's probably something related to their halo properties. And I think that is something that we can learn about, say, environmental quenching at lower redshift from higher redshift, is that because we already know that redshift above 1 and even like higher, the environment is different. It's like, not the ICM is not strong enough for doing some processes that we see already at lower redshift. So if we can already separate that by understanding them at higher redshift, and then I don't know, if we can identify, like, okay, at which epochs, which processes are dominating, that can help us to understand, okay, then which processes stand out at lower ones. That's what I think.
You can say something coherent after all the food of the week. Now, I just want to stress that I fully agree with what she just said. I mean, talking about what we call usually environmental effects only makes sense at low redshift, as it makes sense to ask ourselves, when do these environmental effects kick in? When does run pressure start to be important? When does any other environment start to be important? At high redshift, by high redshift, I mean redshift 4, 5, higher, now really high redshift, the very concept of environmental quenching, in a sense, has no meaning, because it's not a matter of environmental effects anymore. It's a matter of that where the galaxy kicks off, that matters. Do you call it environment? I'm not sure. It's not an environmental effect, but it's very important because the environment at high redshift is linked to the environment at lower redshift, because the highest density region with a great scatter, but the highest density region at high redshift are more likely to end up in a higher density region at low redshift. So in a sense, at high redshift, I will say something now I don't care about environment, but I care a lot where the galaxies are born and the physical conditions where they are born, which is of course what we are talking about. So to be a bit maybe too strong, but I would say we don't learn about redshift zero environmental quenching from studies at high redshift. We learn something very different and maybe even more important. Of course, the lowest redshift studies are easier, but I've seen some wonderful results at high redshift in the last months, and I think we are starting to see what she's talking about, which is great.
Actually, I wanted to raise a little caveat about the quenching at high redshift, because we are always thinking about quenching as a irreversible process. But if you look at the quenched galaxy at redshift 3 or 4, who can tell that it's going to keep quenched all the time? So when you think about the quenching at high redshift, probably might be in many cases a temporary thing. And then environmental quenching happens later on these galaxies that regrow the disk or keep the old population inside. So I think this is adding a further degree of complication in all this analysis, right?
I agree for low mass galaxies. For the rare massive quenched galaxies that we're finding at even higher redshifts than we kind of expected, there is a limit on how much they can grow. There's a limit on what kind of abundances we can have, at later times that they need to match. So I agree that it's a big problem that some galaxies might be rejuvenating, but I think if we look at the very massive end, we can say a little bit more and not worry about that too much.
Yeah, Stefano, were you referring to something like rejuvenation or something more drastic,
At this high redshift, you can just stop star formation for 100 million years,
okay.
And that is what people is calling quenched, because the timescale are so short. You don't measure emission lines, so these are post-starburst in the spectra, and okay, that's fine, but it can happen then you start forming stars again. I don't think we have a clear idea that those quenched galaxies are really quenched forever.
Well, so that, if you want, it kind of touches on something that I was going to say in response to what Bianca was saying, and So we have some pretty extreme populations that seem to live in very preferential places. The kind of galaxies that are forming stars at extreme rates and very luminous and kind of seem to be the signposts of the most massive halos. So those guys, their environment does matter. They're sitting at some node, some filament that's feeding them at some tremendous rates, and they're going to turn off earlier just because they can't become the most, massive thing that breaks lambda CDM or something. So we do have some populations at high redshift where I would say that their environment is kind of their defining feature. And then they will be the first things that quench, and they will have to stay quenched because they can only be so massive. So, but those are extreme populations. Yeah. But maybe they're a boundary condition, I don't know.
So yeah, on this, I think that there's a very interesting connection with the environment for these very massive galaxies at very high redshift. And I do think there is a bit of a problem with definition, so maybe we should talk about satellite quenching versus environmental quenching, I don't know. Because one thing I found really interesting is that some simulations, I think, are predicting that these massive quiescent galaxies at redshift 4 are actually in a more isolated environment. I think the Magneticum people are finding that. Maybe we have some here, I don't know. Because that is the only way you can actually stop further rejuvenation or further star formation, which is completely the opposite of what I would have expected. But no matter what the truth is, what I find interesting is that suddenly environment is extremely important to understand the most massive galaxies and what happens to them. So it's not because the gas is stripped or anything like that, but I would still call these the environment, I think, and it plays a central role in understanding these earliest massive galaxies.
Mass and environment are even more related at high redshift. So.
Yeah, so I was on the paper that was quoted earlier. So I would call this environmental aided quenching. So these galaxies that we found are, they are local nodes, but they still are in very tenuous environments, and the filaments that feed them, I think I showed in the movie also that we found that they can disrupt them with their feedback, so they can just stop the flow, blow the filaments apart, because these filaments are not very strong yet and not very evolved yet. So this is how they cut off basically their flow of gas onto the halo. So I would also agree that it is not the environment that quenches these galaxies, but it helps them basically stop their star formation process.
But they couldn't have that kind of feedback if the environment wasn't feeding them like crazy. I mean,
sure.
I've had a hard time lately separating in my mind environmental things like mergers and gas stripping from triggering of AGN that then has feedback. I mean, these things are, as we've been talking about this whole conference, these multiple things are happening at once, and they're all kind of related, and I'm not sure that we should be separating even kind of things that we usually think of as secular mechanisms.
Yeah, it's a good point. They need their massive inflow of material to trigger their starburst, as I think I've shown yesterday.
Oh, sorry, you had your hand up first. I'm sorry.
Thank you. There's a lambda CDM technique or effort that I think might be useful to link these two redshifts. That technique is to reconstruct the large-scale structure of the universe at different redshiftless slices. For example, it reconstructs the coma, the filament and the coma substructure itself. Because for our observation, the difficulty we often have is about the progenitor problem as well as the orbits that matters much. But the simulation, particularly lambda CDM, they are weakly in the bion physics. And if we take their merger history, their hierarchical history, and use our observational information of different gas species, I think linking these two redshifts, that would be very powerful.
I think it will be interesting for sure, but it's already hard to define the filament today. That trying to reconstruct how the filament was in the same filament evolved in the past is very hard, because for groups, clusters, at least simulation can tell us when the galaxy first crossed the Villiers radius, or you have some definition. I think that for the filament, trying to figure out how the spine evolved and which are the galaxies that belong to the filaments at different epochs
it's a philosophical question, I think, at this point. We really don't know what the filaments are today, that trying to figure out what they were in the past. Okay. And the velocity, three-dimensional velocity. Okay. Yeah, okay.
I think we have to stop so that we don't go over coffee, but don't get up yet. First, we're going to thank the panel. And so Bianca studied at a classical high school in Pisa, and Marco, not me, asked her to help with this translation. Tell us. High quality Pisa.
I think, but Alvio, help me. Your Latin is surely better than mine. The rarest, the better.
Yeah, the rarer the better. Or, cast in the language of this conference, gas jellyfish galaxies might be at the high mass end and in the most massive clusters, but they are awesome.
Yesterday you told me this.
It was his idea. Thank you.
Please come back at 4:15.